Hello, everyone. Good morning.
Good morning.
This is week 11, and today we are going to look at the graph data structure. Now, I'm going to just give an overview of what we did in the pre-recorded videos, and then we'll try to look at a real-world example and try to create an app or a solution to a real-world problem using the graph data structure. We have learned that a graph is a non-linear data structure. And when you have a graph, you have the nodes and you have the edges. The nodes, we call them vertices, and they are like the different entities in the graph. And then the edges are the connections or the relationships between these vertices. So every time we have a graph, we have the vertex and the edges like this. So we have vertices and edges. We have directed graphs, we have undirected graph. In a directed graph, the edges have direction like this. You see an arrow, A to B. In an undirected graph, the edges have no direction. All right. Has everyone seen the pre-recorded video?
Yes.
Okay. We also have weighted graphs that have weights, both the cost, distance, time. And I think we'll look at the weighted graph in more details in week 12. Then we have unweighted graph where all edges have equal weight. We have cyclic graph that contains at least one circle, and we have a cyclic graph that contains no circle. We have connected and disconnected graph, and we say a graph is connected if every vertex is reachable. All right. So in Python, the most common representation of graph we use is adjacency list, which is when we have a vertex and then we have a list of adjacent vertices. But we'll have the matrix also, where we have it's like this of size. Let's say where the vertex is V, we say of size V times V, like this. So this is what we'll focus on, the adjacency list, where we have a vertex and a list of adjacent vertices. And why do we choose this? We usually choose this because of the efficiency. If the graph is fast, where we want to traverse this graph, it is easier, and then it is dynamic also. So we saw the implementation in the pre-recorded video where we have a graph class, and then we have a class where we can add an edge, and then we have a class where we can search the graph using breadth first search, and then we use the depth first search. And then we did that in both recursive method. Can you also hear me clearly?
Yes.
Okay. So we did that in both the recursive method, and we did that also in when we use the iterative method. Then we also looked at how to detect circles in graph, and we looked at how to detect circle in an undirected graph and in a directed graph. Now, who can tell me what you can think of when you think about a graph data structure? What kind of app do you think will use a graph data structure?
You want to send me?
Can anyone tell me what kind of app you can think of for a graph data structure?
Like Google Map.
Yes, like Google Map, a navigation system. So today we're going to try to build a city transportation network analyzer. Something about transport. We use graph. And what we want to do is, let's say you are a junior software engineer, and you are hired with a company that builds software to analyze transportation network for a very large city. Or let's say something like transportation network for Lagos, for instance. They want to deal with the traffic congestion or something. And we want to create a module that models the city's transport network and will support all the route analysis for the different places. If you're going to this area, how many routes it takes you to go there. So we want to do that. And we want to detect circle, and then the shortest path problem is something we want to deal with in week 12. But if we have time today, we will just do all of that. So next week, when you get the pre-recorded video, you already understand what the shortest path problem is. So the first thing we'll do is to create the graph class like we always did. We'll use the adjacency list. Then we'll look at different methods that we want to add to this class that we're creating. Can anyone tell me what kind of methods you can think of that you think we will add when we create the graph class here? Anyone? Okay, when we talk about network, city transport network, normally when you want to go to a train station or a bus station, any of those stations for the transport, you first of all want to get the station, right? So we'll create like a method to add the station. And then we want to see the routes, like we want to add routes like an undirected connection between two stations. And then we want to see how we can traverse. And when we're traversing, in this case, we are looking for all the stations that are reachable and the routes to reach them. So we're like trying to detect edges. We can use the breadth first in that case, and then we can use the depth first search to inspect the entire network parts. And then if we want to now look at the shortest parts, like the shortest subway routes, the minimum number of hops between routers, and the shortest emergency response routes, and all of those things. That's the shortest path problem that we are going to look at in week 12. And then we can implement circle detection, and the circle detection is just to see if a transport route contains loops. That is, there's a transit loop, there's a circular route, and all of those things. So for you to build things like this, you have to think critically about how a transport network will ideally work. Whether you are going to this bus station, you're taking a bus, and you need to take 3 different buses or 3 different trains to get to your location, and you know, okay, where from here to here, where's the first stop, where's the second stop, where's the third stop for these different trains to get to where you are going to. Or you want to check if there is another path you can take, how many paths leads to the same place, how many routes leads to the same place. And so you want to see all of the different connected edges. Does it make sense?
Yes.
Yes.
Okay. So now let's try to implement this, and we know that only implementation is what makes us understand this better. All right, so say we are creating the graph class. So let's say class graph, and like we did in the pre-recorded video, we want to create maybe a dictionary that holds the adjacency list. We're not going to use a list, to use a dictionary so we can have it as a key value pair. So let's do this. Dev init self dot let's say adjacent is equal to an empty here. So the first method we want to do here is to create a method to add a station. So we'll say def add station like this, and we want to pass in the station that we want to add here. Then now if the station is not already here, then we want to add that station, right? We want to check if the station is already in that graph, and if not already there, then we add station. All right. So now you say if station not in self dot, if the station is not here, we want to now say self dot. So now this station is the key, right? Is now equal to. So what we are doing here is we're adding it like a vertex, right? Is equal to now that list. Now, do you understand what I just did here?
Yes.
Yes.
Okay. Because the adjacency list where we have is a vertex and then as a key, right? And then we have a list of connected vertices as the value. The value is a list, just like we have here. So we have that here and then the list of connected. Now we want to add a root, right? Def add root self. So when we're adding roots, we are going to like we're creating a station if a station is missing, and then the station is missing, and then we add that station if it's already if the station is missing. I'm trying to think of a better way we can do this. So you see in the pre-recorded video where we add vertex 1, vertex 2. So this is just going to be like the add vertex. So the station is the vertex, and then the root is like the edge or the list of connected vertices. Like we're adding edge. So if you look at the pre-recorded video, the add edge method we created is just like we're adding roots, and the add vertex is this. So we'll use this add station here to create a station if it doesn't exist. So we'll add the station. So let's say we're adding, let's call this A vertex 1 and vertex 2, AB like this. And then we'll say if A is not in self dot, let's post the, if it's not in this, right, then we want to add it. So we'll say self dot add station A, and then we'll do the same thing for B. Okay. So now we are doing this in an undirected graph, right? So we want to say self dot adjacent A dot append and then we'll append A for undirected graph. So let me explain this again. So what we are doing here is we created this add station, which we are going to use in the add route to add a station if it doesn't exist. We are trying to do this adjacency list where it has a vertex, and then that vertex is the key, and then a list of connected vertices. So for instance, if you look at the pre-recorded video, you will see if it's undirected. So when we're doing undirected, so you now have B and C are like adjacent, or they are vertices that are connected to A. So you can now say that from A you can get to B, from A you can get to C, like that. So now what we are trying to implement here is we want to add a route, so from point A to point B. So we're putting this A to B. Let's use a live example. Let's say you want to add a route from, let's say we have a town called Newtown, and we have another town called Old City. You want to add a route, that the path or the routes that you can take from Newtown to the Old City. So let's say, so we're always, a route is always between two places, and so we're adding routes from point A to point B, right? So if A, that is that A, so when we say from point A to point B, these two, A and B, are called vertices, right? And so we want to check if that vertex is already in the graph dictionary here, if it's already a key in that dictionary. So if A is not in that dictionary already, so if it's not already, doesn't exist, because we don't want to have duplicate key, right? If it's not already there, you want to, so we're using this add station now to add it there. And what this does is that it adds this as a key, and then it will now add a list of connected vertices, like all of the routes, or all of the vertices that has a direct connection from A to B, and or there's a route or is reachable. Then if B is not there, you do the same thing. Does it make sense?
Yes, yeah.
Yes.
Yeah.
Okay. So by the time you add A and B here, so it's like you're having a key A, and then you have a list of connected vertices, and then you're having a list B here, and then you have a list of connected vertices. Now, what it means here now is that when you append, for this you append B, for this you append A, is so you know that there's a route from A to B, there's a route from B to A. So that's what we just did here. So what we're doing is just like an undirected graph. So does it make sense? It takes a lot of thought process to think it right. Now, we want to see how we can traverse. We'll use a breadth first search. And what we said we wanted to do with the breadth first search is to we can use that to do the shortest path problem also, but the shortest path is something we've not discussed yet. So I want to see if we can let me see what we can do with this breadth first search. We can traverse through it, but we want to also make sure that the stations are reachable. And so we'll use the breadth first traversal like we did in the recorded video. So here, let's say we want to put the starting point, and let's do it like this: def breadth first search self, and let's say start. Okay, so let's see the different routes or the different paths that are reachable. When we go through point A to point B, we want to make sure that we keep track of where we have visited the paths we have traversed before, so we don't do it twice. So let's call this variable visited, and we'll store it in a set, set to remove duplicate. And then we want to use a queue, and let's say queue is equal to start, and let's create the order is equal to an empty list. So let's say while queue, I'm going to explain this better once I finish thinking and writing it. So while queue, when we use a queue, is first in, first out, right? And so we want to pop the first index position. So we'll say node is equal to queue dot pop 0, and then if node not in visited, visited.add node order dot append node. So we want to make sure that while we have items or where we have vertices, we want to start from the beginning. So it's a queue. The first thing is the first out, right? So the node now will now be the first index position, the first one in, and once you have already popped that, you want to mark it as visited, so you don't do that first vertex again. So if the node is not in this visited, so you want to add it, you want to add that here, and you want to append to this order, or to this list here, that node that you pop out, right? And then let's look at the adjacent vertices for this vertex, the list of adjacent vertices. In the pre-recorded video, we call that iterator neighbor, but I'll just use MBR, right? In self dot adjacent node. So if it's not in visited, we want to append it to the queue. Okay, so let me explain this better. Let me think of a way to explain this so that you understand it better. So we're trying to traverse through this graph. We're using a breadth first traversal. And when we use this, we're using a queue, right? When you want to traverse, you have a starting point where you're starting from, and then the different connected vertices. So we're just looking at, Newtown. That's my start. And then I want to start traversing to Old Town. And there are several towns I will pass through on my way to get to Old Town. From that new town, every town I get to will be a vertex, or will be a node, right? So from Newtown, let's say I pass through 5 cities before I get to the old town or old city. So those 5 cities are the different vertices that are adjacent, and the connection between Newtown and first city, second city, third city are all the edges that we're going to have. And so what we're doing here is, when we visit a particular place, so we have gone from Newtown, we've seen the first city, city A, let's call it city A. We want to add A to the visited list, just so that we can always check this to make sure that if we are going from Newtown to another place and we're going to pass through A again, we don't want to add A to the list because we've already done it already. So you just want to add this, want to make sure it's unique. So that's why we use a set. Now for the queue, we are creating a queue of like all of the vertices. So it's going to be like the list, and we only have the start point. And so we're going to be adding all of the cities that we pass through in this list. And then this order here is going to be a list of the place, just the path we pass through, just the way we pass through it. Okay, so like index position 0, the first place, index position 1, the second, third. So just like that. Now we're going to just loop through this queue to see where we have any item here. We want to pop first in, first out, and when we pop 0, it will return whatever the item or the value there at that index position 0, which is the first item, and that is going to be a node, right? So the start is going to be a node. Now we visited this node because we've popped it out, but we use this pop to store it here, and we want to make sure that it's not already visited before. And so we'll say if that node is not already in this visited, we want to add it here so that we know that we have already visited that node and we're not going back there. And then for this order, we're going to append it to just show this is the first place we made, the second place, the third place. Now, do you understand it?
Yes, getting it.
Yes.
So now we want to loop through the graph that we have here. We want to loop through this graph. And so this iterator, you can call it I if you want for I in, but I just call it neighbor so that it just illustrates what we're trying to do. We're looking for all the adjacent vertices, the list of vertices that are adjacent or that are connected. So we want to say for that iterator in, so the node we have now, we want to look at the graph. So this is the key. So this is the vertex, and we want to get all of the connected vertices, just like we have here, and the connected one. And so we'll say if that particular item that's pointed to here is not already in the visited, we want to add it to the queue. And so that's how we put the queue. So start, then the next thing we'll have is that item, and we'll keep having, and then it's going to continue to repeat while we have item in this queue. It's continuing to loop this until it is done. Okay, and then at the end of the day, because we'll always return the order of the visitation here, this is what we are returning, the order. Everything about this queue and the visited here is just for us to use it, not to visit an already visited node, to just be in a loop, and you won't get a correct path. And everything in this queue is just for us to have all of the vertices and the connected vertices, and then this order just gives us, we go from point A to B, we'll just get a list of all the vertices here in the order, and then we'll return it. Does it make sense now?
Yes.
Okay. Now we want to do, let's see, what's the next thing we want to do? So this one will give us all of the reachable stations that we can get to, all the stations we pass through to get to our location. We want to implement or inspect the entire network path, and then we can use depth first search to inspect the entire network. And how we're going to do that is to, let's say we will, just like we did in the pre-recorded video, we can repeat the same thing. So if you understand the pre-recorded video, you just apply those different methods to the solution you're trying to create with slight modification to fit it. So let's say depth first search, self, start, and we'll set visited to none. So we'll say if visited is none, we want to say visited is equal to set.
Excuse me, Miss Julia.
Yes.
For the previous function, that breadth-first search,
Yeah.
uh, until we reach to the if condition in that for loop for
Yeah.
the adjacent node, that one. So
Yeah.
that node will be always visited because we are adding it at the line number 45, right?
Which one? This
Until
node?
we yes, until we reach the line number 48 to check there if it is in the visited, we are adding that one at line number 45 before
Yes.
we reach there.
Yes. So no, this one, right? When you get the node, yeah, you're always getting the first item, because now is a queue, right? So it's like you all come to, maybe they say everybody should line up somewhere. You're waiting for service. It's the first person on the line or on the queue that's attended to. So we want to get what is the first thing in that queue, and we'll store it as a node. That's the node. And every time you do that, it means that this one, that's why I say we use pop. Then the next one will now be the first, because now this is a node. You want to make sure that you don't visit an already visited node, right? And so that's why you store it in a set. You will add it, this set now, you add that node here. So even when you try to repeat this and add it here, it doesn't add again because it's already visited. And then you see that when we get to line 48 here, when we are iterating through the graph, we want to get all the adjacent. We will always ask that. So when we say neighbor is like an iterator, so when you get to the graph here like this, what you are looking at is this key, right?
Yes.
So when you come here and say if neighbor not in, so now we will take the key, and when we get this place, we want to look at the list of connected vertices. And if that item pointed to by the neighbor is not already in the list of connected vertices here, that's what we are doing here. So if it's not already there, then we want to check if it has been visited before. So we'll now say if that particular vertex has not been visited before, that's when we'll add it to the queue, because if it has been visited before, that means it's already in the queue. All right. So if it has not been visited, you add to the queue. But what you're asking here is it will continue to add that node to visited. Yes, it will continue to add, but because it's a set, it will not add duplicate. So every time
in the second condition, we are checking the key.
Yeah, we're checking the second condition, we're not checking the key, we're checking the value. Because see, now when you have adjacent node, the key is a node, right?
Right, yes.
Yeah, the key is a node. And so we're looking at the graph, the whole dictionary. So when you put a dictionary,
Correct.
so you're checking this is checking the value. Sorry, that is checking the value. So it's like this, you have this. So this is the key. A is the key, and these are the values.
Correct.
So if you want to check this value now, let's say this is the graph. So you put graph A to get all of this list of the values here. And that's what we did here. Now it makes sense. It's kind of complicated to think about, but when you go through it over and over again, or you try to use a real world part, like real world names, so it will now make more sense for you to understand how to traverse. And that's what I did the first time, to see, okay, for in your case, Anna, you can see, okay, from Grosile to Castries, how many cities are you going to pass through, and make all of them like a part or a name or a vertex, and try to implement how to traverse through. How many roads do they have? Do they have back roads? Do they have shortcuts? Are you going to go through the back and go through Corinth and come out? Are you going to go straight? You understand? So you can do those things as parts. Then when you plot it on your paper as with real world parts, then this will now make sense and say, oh, that's why we pop, that's why, and then it will just stick completely.
Okay.
So now it makes sense. So just think of, so for everybody, just think of 2 places you understand the routes very well. So if you are going from your house to an office, or you are going to drop children in school, what cities do you pass through? How many bus stops do you pass through? Use the real names and just draw a route on the paper and see how you code that route, and you come back to this.
Okay. Yeah. Thank you.
Okay. So we want to say if the visited is none, we'll just do the same thing of storing this in a set so that we can know what nodes we have visited. And then we want to add the stats there. And then let's call this the queue. What we did here, we can do the same thing here. Have the queue is equal to start. Well, let's give it another name here. Let's say visited is none. We create the set, and then let's say visited dot add. Let's add that stats. We'll test this to see, and when we have a mistake, we'll be able to trace it back. And then results will now be equal to start. Let's do it like this. Let's also do the adjacent. Let's look at the adjacent vertices. So we'll say let's say for neighbor in self dot adjacent start. So this time we want to say, if we check the visited and say if that particular key is not already in visited, then we want to add that to the result list. Maybe we'll do it recursively. I'm thinking about another way. So recursive will be shorter for us. So let's say if neighbor not in visited, then we'll have results dot extend self dot the node visited. Then we'll return the results. Okay, so what I'm trying to achieve here is we want to get we want to do something that we can use to get all of the connected parts, right? What we want to get the most is like the whole network part. We're like inspecting the whole parts in the network. And we set visited to none as a default. And so for the first time, if the visited is none, we'll create a visited set. And then the stats where we start from when we're inspecting the network. So let's say you have the whole network already from the breadth first search of how all the road networks to a particular part. And when you have this road network, you want to now inspect this whole network, and you have a start point, and you want to set all of the parts you have already visited to none, because at the beginning you've not visited any parts. And if it is none here, you create an empty set where you store everywhere you have visited. So the start is already visited by default. Once you start, that's already the starting point. So you add it to the visited set so that you can use this to check if you have visited this node before. Now, the result is like you are creating the order, just like we did here, where or you're creating the queue, where you put in the start. Right. So you want to have the queue of all of the network parts. So it's going to be a queue. So it's going to be in order of first, second, third, fourth, like that. So you want to now loop through the entire graph, right? You want to loop through all of the adjacent, the list of adjacent vertices like this. You want to loop through this list, and you use the node as the key to get to the list. And you want to say if that's what is pointed to, the item pointed to here. So we can use neighbor, we can use I. You can use I here, so that you know that this is not like it's any variable from anywhere. We'll just call it neighbor to illustrate what exactly we are looking at. So if I in that graph already, if I is already in the list of adjacent vertices to that vertex, and we have not visited I, then we want to recursively do this. So we'll say result.extend self dot, we call this recursively, and we'll provide the stats, and we'll provide the visited already, the nodes are visited. At the end, we return result. So when we use extend here, is what we use to join two. We used to join two lists or two together. So we use it to extend. We use extend methods. So we look at the different methods that we have. So we just do it recursively here, so that we can do this over and over again until we have inspected the whole network, and then we'll return the result here. Does it make sense to everybody?
Yes.
Yes.
We can also do the shortest path to get from one node to another. Since we have not addressed that, is week 12 topic, we'll leave the shortest path method, and then we'll do it next week. But let's look at circle detection. And who can tell me why we want to detect circle in this whole problem?
Will you please repeat your question?
I said, who can tell me why we want to implement circle detection here, and what we are going to use the circle detection to do? Anybody?
Sorry, couldn't figure it out. No.
Okay.
I think from the class video, we talk about circle detection is when we have already visited and already, that's when we revisit and already visited the node. So I don't really get it much. Yeah.
Yes, so that's want to see if the transit contains loops. Like if you go from, if for instance I come from the new town and I'm trying to go to old town, and I take a particular path, if it brings me back to new town, so if it contains circular routes, so you see sometimes when you go to a new city and you're trying to use GPS, like okay, for those that have been to Boston, you know that GPS will throw you off. You pass the same place you've passed several times. You see yourself driving for up to an hour, and then you see a building and you say, I've just passed this building the other minute. I now notice that you take this route, you're just coming back to the same place, and you can't find an exit to go to another city. You want to see if that transport route contains loop or any circular route, and we're going to detect the circle here to see that. So let's say dev has circle self. So visited will always be a set. Let's create another function within this function, another method inside here. And so the inner function will be dev DFS. So you can see where higher order function and all of those different things we learn in Python Fundamental is coming in. And closures too. The TFS circle. Now you can absolutely do this in a different way. If you can think about it well, you can try to implement it in your thought process and see if it gives you the same thing. So visited.add node. So we're just repeating the same circle detection we did in the pre-recorded video, where we want to return a Boolean true or false if we find a circular node or a circular root, and we'll return true. If not, we'll return false. So let's say for the neighbor in self.adjacent node, if the neighbor not in the visited, we will say if ZFS circle I will explain this again. Let me just write down the thought process and then I'll explain it. Return true, and then let's say Elif here. So what I'm trying to do here is I want to have this, I'm doing this as like a closure, like I have this inner function here where I want to use to check if there is a circle detection. Now the parent is like the first vertex or the first node, and if we have the visited set here outside here, and we want to say if when we come into this inner function, we want to add the node, that's the first node there, to the visited this, so that's because we're already on the first node, we want to add it there so we don't visit an already visited node. And we want to now loop through that graph to say for the iterator in the graph, so when we loop through the graph, we're looping through the adjacent list to a vertex, right? So for that adjacent list, so we're saying for now, because we have a node, the node is going to be a vertex here like this, and then we want to use it as the key in the graph. Because when we create a graph, we have a dictionary. Dictionary is key value pair, right? The key is that node, and then the value is a list of other nodes. So here we're going to say for the iterator in that graph, so in the list of adjacent vertices, we want to say if that item pointed to by this iterator is not already in the visited, then we want to recursively call this function and do the same thing over and over again and return true. So if it is not in visited, then we call this function recursively, we return true, because if at this point, if it's not already there, it means that if it's not already there, we recursively call this function our node parent, and then we return true, which means we have detected a circle. And now if it is already in the visited, right, and it is not equal to the parent, then we going to return true. Do you understand? Because for a circle detection, if a node is not equal to the parent, then it is a circular graph. Let's go back to the pre-recorded video, and I will give you the rules about circle detection. So you can know when you're writing your code and you already understand the rules. I mean, does everybody understand what I'm trying to get here? I don't think I'm explaining it as good as it should be.
I understand.
Understand?
Yes,
Okay.
getting it.
So we detect a circle if we revisit an already visited node, right? And we detect a circle also if that node is not the parent of the current node. So there are two things you want to check for. And this is because it is an undirected graph. Right? But in a directed graph, if we visit a node that is already in a recursion stack, then it has a circle. So the two reasons or the two ways we can say we have detected a circle if you go to your pre-recorded video or your lesson notes is when you revisit an already visited node. So that's why we have the condition here. First of all, is if it's not invisited, we want to recursively call this inner function, right? And if we call this inner function, we return true because now we are visiting an already visited node. The circle is detected. Now, if it's already invisited, right? If it's already invisited, we want to see. So we are visiting an already visited node. But when we visit an already visited node, and the node is not the parent of the current node, then it is a circle. So we now say if that node is not the parent, we have detected a circle. And at the end of the day, if all these conditions are not true, like all of these conditions do not evaluate to true, return false, there is no circle detected. Does it make any sense?
Yeah.
Yes.
So if you look at the undirected graph circle detection we did in the pre-recorded video, it's just the same code we're writing here, but like we changed the variable name to make it close to what we're trying to explain. Let me think of anybody understand, or you want me to really explain the whole logic again so that you can understand it better? This is a thought process that you have to study very well for you to really understand the thought process. Anyone?
Maybe just one more time.
Okay. So let's even start it from the beginning so we can understand the flow we are trying to get here. So the whole idea is that we are trying to analyze a transport network in a city, right? So let's say we'll say junior developer because we're not going to do things in a very Pythonic way. And we have this city, or let's say we see a desert land or a new land that we have somewhere. We are stuck on an island. We go into the island, into the part there, and we see different places. We have waterfalls. It's just an untapped place. We see different things there, and this island we're just lost at sea, and we ended up on an island. Nobody inhabits the place. We want to turn it into, let's say we have a whole ship of 1,000 people. We want to create our own new country, or we come together to create a whole government system. And say if we want to start, we'll have a leader. We want to start building the city. This is going to be our little country, and we're going to institute this as a country. Now we want to start creating landmarks, right? And you see different parts. You see in this place there's this waterfall. We give it a name. We'll go to this place. We'll see a stream. We'll go there. We'll see a boiling lake, and we'll say we want to name all of these places. We want to create a path from all these places. With time, we want to have bus stop, and then we'll build this city, and we'll have different places that we have named. And now we want to create the transport network for this city that you've had, so that you have a guide. Maybe you now have a city hall. You want to have everything. Now, why do we have a transport network? Let's say you have emergency service, fire service, you have ambulance. If anyone makes a 911 call and you're going to go to the address that they have asked, you need to have a city analyzer that the ambulance are programmed with, or the fire service is programmed with, where at first, when you put the address, it gives all of the networks automatically. It's almost going to be like a GPS, but in this case, it's specialized in such that It specialized to that city and knows every single landmark in the city, the places you can pass. If the city has created roads and the road has a lane for fire trucks, let's say it's a burning house, and they have different fire hydrants and different place where water source, and they can now look at that graph immediately and see this is the place we'll go to, because through this part we're able to get here. If we go through these routes, the fire truck cannot easily access the building. If we go through the back, so you see it gives you all of the analysis, and so you want to create that network analyzer. Okay, let's call this our network analyzer. Let's call this name of this company, our software company, Urban Flow. And what we want to do is to create a network graph for it. And sometimes you create this graph where you have not even created the transports, just the names of the city, and you want to start putting bus stops. You want to see the different places to put bus stop, the different cities that are reachable. If you say you want to go to the Boiling Lake, for instance, you want to see that, or you want to go to the let's say the Boiling Lake, for instance, we know that there's no motorable road to that place. There's no path to it. And so when you want to traverse, this place has no path. You see the last place you can stay before you start hiking to the place. Do you want to create a path to it? Do you want to say we want to create bus stops and paths to this, so that when we're doing tourism, people can come up there? Do you say we want to go to another different place? Is it reachable, the traversal? So when we use the breadth first traversal, is we want to see all the reachable nodes, right? And so that's from point A to point B. What are all the paths that we can go through to get all the reachable stations? And then we want to when we want to inspect the entire path is where we use this depth first search to inspect the whole path, the whole network, right? And this is what we even use when we want to use GPS and see the shortest path to somewhere. Now, if, for instance, if you see GPS, sometimes it will tell you, because of the traffic on this point, there's an accident on this road, on this route. It will take you 10 minutes. It recalculates that. So a journey of 2 minutes becomes 10 because they stop. Or they'll tell you that there is a fire service there, or there's a police there checking people. There's a stop and search going on in a particular place. Somebody must have entered that. The GPS immediately starts calculating an alternate routes for you to follow. There's an accident on this route. Well, because you have a network analyzer now, it knows another path you can use to go from point A to B. And so now here you can say, okay, you want to get to C from point A, but you know you can go from B to C. So let's see another route where we can follow from B to C. So we're now seeing another path to get to C through B, or we don't have to go through A, right? And from C we can get to other cities. Let's say we can get to D, E, F, and let's say, for instance, what we want to get to is F, and we'll have a node where we can start from C, then go there. So this is the whole idea. So I want you to use cities. You just take a pencil and a paper and write down the names of cities, or a place you frequently go to, and see how many places you pass through before you get there. If you are traveling from, let's say we are traveling from, let's use Nigeria to the Caribbean, for instance. You are going from Nigeria to, let's say from Nigeria to Grenada, for instance. You know that there is no direct path from Nigeria to Grenada. There is no direct flight. And you have 3 different ways you can, or 4 different ways you can get there. Do I want to go through South America? Do I want to go through North America? Do I want to go through Europe? Or do I want to go through Germany? Do I want to go through United Kingdom? So you now see that there are 5 different connected vertices, right? And so now Nigeria will going to be the first point, and so you can get from Nigeria to London. That's a city you stop in. That's route A. London, you can get to Barbados. Route B, Barbados, Grenada. So you see the path you have gone through there. Or you can come from Nigeria, you can go to a country, South America. Maybe you want to go to let's say Brazil or somewhere there, and then from there you can get to Barbados and get to Grenada. Or you can say you will go from Nigeria, you go to Atlanta. From Atlanta you fly straight to Grenada. You see 2 cities, 2 stops. Or you can go from Nigeria, you want to go to Florida, or you want to go to New York, and then from there you want to fly straight to Barbados, then Grenada. You see the different paths. Or you want to say, okay, there's a direct route. Nigeria, you go to Frankfurt. From Frankfurt straight to Grenada. Nigeria, you want to go straight to London. From London straight to Grenada. So you see the different paths that you have. So because you understand the routes or the different place, so what you can do now is to try to use flight routes for those of you that travel a lot, or you want to use the route from your house to your office to your children's school, to see, like, you need to drop your children in school and you need to get to the office, and maybe there's a route where you pass through your office before you get to their school. And so in the morning, you drive past your office and get to their school and drop them and drive back towards your office. Or there's a route from your house where you can take a back road and you get to their school first before you get to your office, so you don't pass the same route twice. So you see the whole thinking. So before you build an app, sometimes you want to understand the domain. You want to understand transport system. So if they tell me to build a city transport network analyzer, it will make sense to me at first. Once you understand, okay, what do they want to do? Urban flow. You want to see the flow of network. What is the end purpose of this? I want to see how I can get from point A to point B. What are all the paths we can take to? What is the shortest path, the shortest time? And so that's when we get to weighted graph and all of that, where you see distance, time, and all that before you can implement a GPS or to solve like a path problem. Okay. So when we do this breadth first traversal, we just try to explore all of the reachable stations here. And then when we use the depth first here, we just want to inspect the entire network path. Then for the circle detection, we want to see if it contains loop like this. That's why we use this higher order function here, where we did this closure, where we say did this like this, where we said if we visit an already visited node, it has a circle is detected. If that node is not the parent, a circle is detected. If it's not any of those conditions, then there is no circle. Then we can implement the shortest path too. I don't think I want to implement that now until I have a pre-recorded video for shortest path problem, so you can understand, and then we can next week add shortest paths, a method to this. So now, does it make sense?
Yes.
Yeah.
Okay. So now that we have done this, let's try to test this function. And let's hope that, if we have minor errors, it will not, I don't think it will have so much errors. We would be able to fix it. But the whole logic we're thinking about now is correct. So let's say def main. We want to say, let's create a network. So let's call it network is equal to, we create an empty dictionary here to create a graph. So now we want to say the stations. Let's create a station A to F. So now in your own thought process, you want to put real city names or something. You want to create a scenario and put the names of the cities and landmarks and things and see how you can get from A to B. So let's just call the city's name A, B, C, D, E, F. Like this. So let's make it up to F so that we can have enough. A, B, C, D, E, and F. So these are the different stations. And we want to add, so now we have these stations and we want to use this add station method here to add them to the network. Right? We want to add all of this to the network as the different vertices. So we want to add the vertices to the network, and then we'll now add all of the list of connected vertices. So let's say for S in station, we want to say network.add station S. So we want to add all of them, has different keys in the dictionary with empty list of connected vertices. Now we want to add all of the routes here. So what will be the routes that we have? Let's say we have a route from point A to point B. We have a route from A to C. Then let's say we have, let's randomly just create routes for the different points. Let's say these are different names of city. We just use this. And let's say we have routes here to be a list, right? And this will be list of lists. We have a route from A to B. Right, so that's one. We have another connected. Let's do this as not like a list of tuple like this, AB. So I think the tuple will make more sense faster. And then we'll say we have A, C. Now I'll tell you something. Software development involves a lot of thinking, analytic, logical reasoning. And the thinking will be so deep, and the more you try to solve complex problems like this, the more you challenge your brain to be able to think as you're supposed to think, because on the first glance you won't even think about it like this. And for those of you doing internship, you would have seen yesterday when you created I think for Anna, you have seen when you created something that you can use to validate forms. You see that the thought process was basic, and then you start thinking about it deeply, and then your mind opens up to see multiple ways you can explore and create an app that does not lead to a roadblock, or that you can easily add things in the future. You are having forward thinking and things like that. So for this, it might come across as it's difficult, you're not understanding, but it's not about you right now, and it's not about the explanation right now. It's about the power of your mind and how you can challenge your mind to think things in a different, complex way. Okay. So normally you won't think that way until you are challenged to think that way. If you think that way in a normal way, the world will classify you as abnormal. This is one of the weird people, or you are a nerd or something, because you can't think like this in your normal daily life. You can't think anything too deep. But when it comes to development, you have to think very deep. You have to think weird. You have to think abstract. Okay.
Yeah.
So let's have, I'll just randomly put different roots, and let's see how we can use this. Let's say we have from D to E, and then we have from, let's say, E to F. I think let's stop here. And now we have all of these roots, and so you see here when we use these add roots, we put A and B here, right? And this is like the two roots, A to B, point A to B. And we want to put the connected vertices, a list of adjacent vertices to the vertices we already created here. These are all the stations. The stations are the vertices. I want to put the list of connections that we have. So we did this as a tuple so that we can call A and B, just like we did here for the add root, the point A to B. So A to B, A to C, B to D. We want to add all of this to the root. Okay, so these are the roots we have. We have from point A to B. So we want to use the method to add it. So we'll say for A, B in root network dot add root A, B. Okay. Then now, let's say we are printing let's print the all the reachable routes now. So we're printing this one we use for the breadth-first search for all the reachable stations, and then we want to inspect the entire network with this, and then we want to check if it contains circle. Let's do that like that. Let's say print. So this one, what we're doing here now, we want to say reachable station. We'll say reachable station from A. Okay, so when we look at this from A, we have A, B, C, D. So we have A, we have reachable station B, 1, 2, of A to B to C. Let's see how it says. So reachable station from A, and let's go network dot, we have breadth-first search, and then we want to supply the A here. Okay, because here we put the start is A, so reachable stations from A. Let's do inspect the whole network where A is the start also. Let's say inspect network. So we inspect the entire network part, and we are inspecting from A. So for to inspect, we use the def first search, and we're doing from A. And let's see, does the network have circle? Let's say so we'll say network dot has circle, and we don't supply anything here for circle detection. Let's see, yeah, we don't supply anything. So let's see if this works, and then see what error we will get, and then we'll retrace. Sorry, this print is supposed to be outside of all of this. Oh no, I put the print here in the function. So let me just do if name equal to main. Sorry. If name equal to main, then we'll say main. Okay, and I did it this way because I created def main here. So sometimes when you want to do this for testing, this is what you do. So this is like the testing session. Let me do it here like this so you know. Okay, so this is like we'll create this as a function, and then we can call the main here. So it's easier that way. So when we run this, name station is not defined. Let's see why name station is not defined. Oh, sorry, this def main is going to be, yeah, it's outside, right? It's outside this here. Name station is not defined on line 93.
It's stations, the loop, I guess.
Okay, stations is the name here. So for this in stations. So you see, that is where we always have a problem. All right, thank you. So I'll clear here so you can see, and then I'll run again. Okay, now it works actually. So reachable stations from A, B, C, D, E, F. Inspect network paths from A, B, D, C, E, F. So can we see how this works in real life? So the stations we have is A, B, C, D, E, F. Now, when you run the code, from A, you can get to B, right? From A, you can get to B. Which also means from B, you can get to A, right? Now, from A, you can also get to C. So this is how it will be. And then from B, you can also get to D. Now, if you can get to D from B, and you can get to A from B, it means that from A, you can also get to D here. So this A is connected to B. And because it's connected to B, you can get to A and D, where is B. So let me do it like this so you see how it will work out. So we want to manually do it and see. So you can get to B. From A, you can get to C. From B, you can get to A. You can get to D. Right? From C, let's just do it one and then we'll now go. From C here, you can get D. Okay, and if you can get D from C, you can get from C to D here, and then from D, let's do the first layer. Then we'll go back. D, you can get to E, and from E, you can get to F. Now let's go back. From A, you can get to B, which means from B, you can get to A. From A, you can get to C, which means from C, you can also get to A. So add it here. Okay. From B, you can get to D, which means from D, you can also get to B. So you see what I'm doing?
Yes.
Okay, so from A to B, B to A to C, C to A. B, you can get to D, that means from D, you can get to B. From C, you can get to D, which means from D, you can also get to C. All right. From D, you can get to E, which means from E, you can also get to D. From E, you can get to F, which means from F, you can also get to E. So you see what we have done here? So we can see the path here. Now, if from A, you can get to B, and from B, you can get to A and D, which means you can replace this B with A and D. So this is a path to A, right? A, you can get to ADC, which means that B here, you can get A here, which makes you ADC. You understand? If A is ADC and C is AD, so you can do ADC here also. So D, you can get to BCE, so you can replace D here with BCE. And we already have C, so we'll not repeat it here. So D here with BCE, so we'll just put BE. All right, and D here, we'll call it B. D here will be B E, and then here we have D B C E, and then E D E F. D here we change this to B C E. So you see that, and then E here, F here is going to be E, which is what give you access to all of this also. Now we can continue to do this in the loop to say here now we say A is A B C E. Now we have it A B C E, so we can reorder this to be C here and E here. Now B here is A B C E, so B here you can change it to A B C E, which is already contained here, so you don't repeat it. Like I said, it's not going to be duplicate. So B here is A B C E, right? So everything you can go from A to B, B to A is now the same. So now, so this is how you do it manually to understand the code. So when you get to C, A is A B C E, it contains A B. Let's order this C E here. So you have A B C E for A, for B is A B C E, for C is A B C E, and so it's now you can get the same thing. Now let's get to D. If you want to replace B here, it's A B C E. So D here will be A will be added here, B C E, and when we get to F, we'll get to E here. Now E is B C E F, and we can come here to say E here is B C E F. So now because of E, you have access to E here, which means you also have access to F here where you have E. So F is here, and so we can get F because of E. Can you see that? We can have access to F. Once you have access to E, E has access to F, and so that means once you have access to E here, you have access to F. Okay, so F here you have B C E F. So because E here is B C E F, so B is A B C E F, right? And I think we deleted D. D is supposed to be from B, we can get to D. Okay, so that's what is missing. Here from B, we can get to D, and which means that because of that, we have access to D here. So you can see we have access to D here. Don't think it too much so you don't get dizzy. D here. Okay, and then for E, you have access to D. So from D to E, E to D. Okay, and because you have B C D E F, B C, so when you have E here, you have access to F. When you have F here, F to E, E to F. So F here, we have access to B because it is here. So say F will have B, it will have C, E, F. If you replace B here with the value of B, it will be A, B, C, D, E, F here. So everything will be in everything. So we'll say A, B, C, D, E, F. Right. So you can see that there's a root. Everything is reachable. And then for E here, we have B, which will give you A, B, C, D, E, F. Everything will now be, there's a root from every vertex is adjacent, has a root to everywhere. Everywhere is reachable. Now, you can see that manually we got this like this. So what is the reachable stations from A? We have A, B, C, D, E, F, and that's why we got it here. When we start reachable stations from A, you get everything. So you see how everything came here manually when you do it. And when you see inspect the network part from A, okay? So when you want to inspect the network part from A, you go from A to B. So originally A has a path to B, right? A has a path to C. A has a path to B. And so where does B lead to? B has a path to D. So you have reachable or inspect the network to be from A to B to D, right? And D, when we get to D, we'll see that D has to C and to E. So we have A to B, because it's A to B. So now we now go from B goes to D. So you go to A to B to D and D to C. So we see D here has to C. So we have A, B, D, C. And does C lead to anything here? No, but D still has to E. So we have A, B, D, C, E, and E leads to what? F. And so we'll see the network path from A will be A to B, D, C, E, F. So that's what we have here. So does network have circle? It returns none, which means that something about the has circle is not working. So we want to return true or false. So we have def have circle, visited set, and we want to recursively call this. Look at the node, the parent. We will say the visited.add the node if the neighbor in the list of adjacent vertices, or for neighbor in list of adjacent vertices, if the neighbor is not already in the visited, we want to recursively call this if DFS circle neighbor node will return true. Elif is not the parent, we also return true, and then we return false. Okay, now here we did not really complete this. We want to look at the stations too. Before we have done everything for the inner loop, but we did not handle the outer loop. So that's why we're returning none. For the outer loop now, we want to say for the stations or for any iterator in self in the dictionary of vertices, if that iterator is not in the visited, then we want to say, let's recursively call this if DFS circle let's say if DFS circle let's recursively call this station and none, then we want to return true, and at the end of it all in the outer loop we want to return false. So we handled the inner loop, but we didn't do the outer loop here. So maybe that's why we have circle none. Let's clear and run that again to see if we get that. So I have to comment this out because it's not part of the code. I'll run this. Now we have, does network have circle? Yes, it has circle because we can see this. From everything we get to the same node back. We know that it has a circle true. So if that was not the case, then we won't have circle. All right. So does everyone understand what we just did?
Yes, it's clear.
Yes.
Yes.
Okay. So this is all about the circle detection and the graph. what we want to do is one thing we want to do is when we get to week 12, we want to see how we can add weights like the travel time, and we can implement the Dijkstra algorithm. We can add closures in the station or recompute routes like we do in GPS. We can also add ability to detect disconnected subgraph or maybe isolated districts or isolated parts. Okay, and if you like, you can even learn how to visualize this in a network graph. We'll try all of that in week 12. Let's see whether we can do visualization also in this to make it more interesting. Okay, so we're going to look at that in week 12. Does anyone have questions?
Nothing on mind.
Okay. All right. In the absence of questions, do you have any question on? I think it was part 2 quiz. What assignment do you have? A quiz, right? Is it a quiz you have, or you have an assignment? You have assignments.
I have an assignment.
Assignment 8, yeah, and assignment 8 is about the continuation of what we did in the last.
Yes.
All right. So is it going well for everyone?
Yes, it's working on it.
Okay.
Yes.
So do you have an overall question in anything that we have done?
Nothing for now.
Okay. So what I want you to do is to go through everything you have done from weeks. I think where do we start from non-linear data structure? And if you have questions, you can organize them, send them a day prior to the live class so we can handle them. If possible, I'll create labs that combine everything for you to really get an understanding. So you see that you get more understanding when we use real world app instead of just learning how to write the code and you don't know how it applies in real life. All right.
Yes.
So you will get your assignment 9 and everything on Monday, and every other outstanding will be graded, possibly, if not by the end of today, before the end of Monday. And then we'll look at different technical solutions for shortest path. And I have a question to ask. Do you guys think that the pre-recorded video and then doing a lab in the live helps, or you want the pre-recorded to have a lab and then during the live class we go through the basics? Which do you think helps you better?
So what we are doing now, it's helping actually,
Okay.
because both covers different topics and different approach actually. So this is helping very well.
All right. All right, everyone. So in the absence of question, we meet again for week 12 live class next week, where we'll hopefully try to implement a GPS. I will see if I can actually create a map of 2 cities that we all know, so that we can use real cities instead of A, B, C, and then we'll see what is the solution it gives us and see if we use Google GPS, if we actually get the same kind of connected paths, so that we can actually know. We just have about 3 to 4 weeks to the end of this course. We have week 12, 13, 14, 15. So we have 4 weeks to the end of this course. And so on the next 4 weeks will actually be really helpful to be a software engineer. And you see that you have different approach to thinking. So you want to really take the time when you have it to review everything you've learned so far. The search and sort algorithms, especially the sorting algorithms, are the different kind of sorts that we will actually never really use in real life because they are slow. It's just for teaching purposes, so that if you try to implement that in your software you are building as an engineer, you will easily know that this is going to be slow, and you can have different ways to do it. You want to use stacks and queues when you are going to be doing searching and or binary. If you want to do search, you want to see when you want to use binary search, or you want to use linear search. You want to look at the different sorting algorithm. You know that Python already has a sort function. All the things we have learned and the time complexity is for you not to repeat those mistakes in your software development. You really will not implement it in your software, except if you have requirements that does not already exist and you want to modify it. And then we'll already look at hash tables, hash sets, hash maps, which you will only use when you want to implement something like a social media network, but you won't actually reinvent the wheel when you already have dictionaries in Python, you already have sets. All right. And then we want to talk about the tree data structure, where we build family trees and connection. We look at binary trees, traversal, and I don't think we did tree in detail, in real detail, in better details in the live class, like looking at the AVL tree and balancing the tree, because we ran out of time. And we'll see whether we'll have a summary live class, maybe towards the end of the course, that we summarize everything in one big app, right? And then we started with its graph data structure this week, after we looked at all the binary tree and binary search tree.
Okay.